welcome back. I hope you got everything right on trivia tonight. I'd like to introduce our first speaker of the night. She is a University of Washington. Oh, wait, before I'm gonna increase the tension. Pause. Before I introduce our speaker, please bring your trivia sheets up to the front where you can see our fabulous trivia czar collecting them. He will also come around collecting them as well if you'd like to keep your seats. Great, so you'll have plenty of time to do that. And in the meantime, I will now continue this introduction of our fabulous first speaker. She is a University of Washington astronomy postdoc and casual gamer who is apparently related to a professional gamer. Fun fact, Dr. Kim Bott.
Hey, thanks very much. So yeah, I'm not like extremely knowledgeable about every single video game, but I am obsessed with a few of them. And I just want to make it clear to the people in the audience that you don't necessarily have to be really into video games to get something out of this. I'm mostly using this as a conduit to learn more about astrobiology, but can I just see a show of hands of who here plays video games? Yeah, okay. Or maybe I should ask, maybe that was dumb, maybe I should ask who here does not play video games? Anyone? Yeah, like tons of people, right? Yeah, I was not allowed to play video games when I was young. I was about, like, I could play SimCity or something where there was like a puzzle component, but most video games were off limits. But when I started playing video games, I saw all these depictions of aliens and stuff in them, and I was already pretty old-ish by that time, so I knew a little bit about astrobiology, and I thought, what an interesting way to talk about what astrobiology actually is, what the science actually is, and how realistic these portrayals of aliens might be. So let's start out with an introduction to astrobiology itself. I like to think of astrobiology in terms of habitability and biosignatures. We're looking for signs of these two things. So habitability is determining whether or not a world is friendly towards life in the first place, and biosignatures would be figuring out whether or not that world already has life on it or trying to detect signs of life itself. Astrobiologists have all sorts of backgrounds. We're geologists, astronomers, biologists, biogeochemists, philosophers, neurologists, or like in psychology degrees. We do all sorts of things and have all sorts of specialties, and it's our knowledge combined that allows us to study what alien life might be and where we might find it. So things that we might be doing might be studying stars and determining how the star affects the environment that the planet is in and how habitable that leaves a planet. We might be looking at oceans and water. How vital is that to life? Where do we find oceans? What sorts of life do we find in different types of oceans? How do we detect oceans in the first place? Can we look for something like the glint? We might study something like tectonics. How vital is that to life? And in what scenarios does that occur? Can planets have surfaces that are just too rigid and they don't end up with the plate tectonics like we see on Earth? We might also do things like study microbes, study extremophiles to see what the limits of life are, so we have some idea of, you know, kind of what's the area we should be searching in the first place, what are examples of extreme forms of life, where can we draw the line. And we might also study things like planet formation to get an idea of habitability. So from what materials are planets forming and what sort of planets do you form from those materials? What sort of differentiation do you get? On the side of biosignatures, there's a little bit of overlap here, but we might be studying things like the Earth through time. So maybe biosignatures or signs of life were very different when the Earth was in its Archean phase a long time ago, when there were different sorts of life. You might expect different signs of life at that time. We might also be looking at what sort of pigments we expect from alien life. Can we detect that sort of thing off of another planet? Or what sort of gases would life release into the atmosphere? So there's all these different parts that go into astrobiology in modern terms, in the scientific study of alien life or where we would find life in the universe. So what does that have to do with video games? Well, as I said, I was not allowed to play video games when I was young. And it was when I was in my mid-20s starting graduate school, which is a very inconvenient time to get into video games. You do not have a lot of free time. I was talking to people and I kept saying, I don't think I actually like video games. Like, I could do, you know, I'm not, like, I could do some shooting, but I don't want that to be the only thing I do in a video game. And I really want to be in space and exploring other worlds in a video game, and I want it to be open-ended. I don't want people telling me exactly what I have to do all the time, and I really want to play like a woman character or a genderless character, and people were like, oh my god, like, we keep telling you about Mass Effect, will you please just play Mass Effect? So I started playing that, and I got absolutely hooked on it, and I was amazed at how accurate, in some contexts, Mass Effect was with its astrobiology as I was going through grad school and learning all this stuff. So I think that this is like a nice way to open a dialogue about what astrobiology really is and how accurately it's portrayed in sci-fi. But it's also kind of important because the way that astrobiology, that the search for life and that aliens themselves are portrayed, oh hi Ted, are portrayed, so I just saw like a high school friend in the back. So the way that like aliens are portrayed and things like that are going to obviously affect the way that the public perceives what astrobiology is and what we're doing. And of course, if you're doing sci-fi, you want exciting things, you want things to be scary, and so space seems like a very scary place, and aliens are always scary. And with the video game side of things, people are often either driving things or shooting things, so you know, you're using like a million guns, like in Destiny or Mass Effect, to shoot aliens, and sometimes aliens are portrayed as these very scary things, and that's just not really like at all how astrobiologists think of alien life. It's a much more pragmatic and scientific approach, as you might expect. First, before I get any more into this, I need to give you guys some warnings. First, please do not play the Bott drinking game. I'm going to say Mass Effect over and over. If you drink every time that I say it, you will be blacked out by the end of my talk. Please do not do that. I also have to warn you, if you're about to play one of these video games, that there are some minor spoilers. There's nothing that's just come out in this. There's no like major spoilers or anything like that. It's maybe one slide for like a couple really old games. But I know it's just like really traumatizing. So I just wanted to give you guys a warning that there are some minor spoilers in here. And lastly, I'm sorry. So I told people that I was doing this. So many of you were like, are you gonna include my favorite alien from my favorite video game? And I'm sorry, I can't cover every single one of them. Oh my god, there's so many video games with aliens in them. And I love them all. And so, you know, just like take a moment to like take in Garrus or little Kerbal friend's face. Just let it soak in right here, because you might not see them again in this talk. And if you want to talk to me about like, well, certainly any character from Mass Effect after this, I'm happy to do that, but this might be the only time you see them. So, back to actual astrobiology. One major aspect of astrobiology, as I said, was habitability. It's determining where we're likely to find life in the first place. And it seems that a lot of people have heard of this idea of a habitable zone. So around a star, we have these habitable zones, here shown in green, where we expect to find water, liquid water on the surface of a planet that's vaguely like the Earth. And if we increase the luminosity of our star, or the heat of our star, I guess you could say, then obviously we're going to need to move further away from the star to be able to maintain liquid water on the surface so that it doesn't all get blown off. And if we have a cooler star, we're going to need to move in so that the water doesn't freeze up. We want these scenarios where we have liquid water on the surface because we think that that's a really vital part of life. We think that that's one of the basic things that life requires is liquid water to be near the triple point of water. And it turns out that Mass Effect, please don't play that game, I'm serious, actually does this fairly accurately. You can't really see here, but I mean, it's not like it gives you the information anyway. But I can assure you there's a star and then there's a few planets pointed out here. And in Mass Effect, you'll typically find like smaller rocky planets closer to the stars. 2 to 4 planets out, you'll find maybe one that might have life on it if you're looking for life. And then further out from that, beyond the ice line, so where the lighter materials have not been completely blown away, you'll still find lots of ice. You'll find giant planets, and that makes sense because you need these planets to be accreting really big cores while their planets are forming so that they can start sucking, gathering all of this gas and become these giant gas planets. And Mass Effect actually does this pretty consistently. And they do have examples of things where you have a planet that's like captured and brought in close to the star, maybe like a hot Jupiter type of thing, or that's migrated in. And so when I was playing this game and exploring all of these systems, as you do in this video game Mass Effect, I was just really impressed that they actually kind of knew about this and included it. And I started to kind of figure out that if I was looking for living creatures on other planets, that I needed to look 2 to 4 planets out, and what was probably that star's habitable zone. So not only does it do the solar system habitable zones fairly accurately, it also does planet habitable zones fairly accurately. So if you have a planet that's maybe a little bit too cold, people wouldn't want to live near the poles, but they might get enough stellar flux, they might get enough energy from the sun, enough heat to live near the equator. That's mentioned in a few different scenarios. And on this planet, in Ilium, we have kind of the opposite problem. The planet's a little bit too hot, so no one wants to live near the equator. So people here either live near the poles or they live in these arcologies, these really tall skyscraper buildings reaching into the atmosphere that provide a cooler temperature for people to live at. So this is all pretty good science, and I was super impressed. I was also very impressed when I realized that Mass Effect actually does the galactic habitable zone fairly accurately. The galactic habitable zone is a real thing. You don't want to be too close to your star. You're going to have stars constantly interacting with each other, whipping planets out of their orbits, messing them up. Lots of supernovae just blasting stuff. So you want your planets to be a little bit further out. And in this Mass Effect universe, as you're exploring the galaxy, you actually do find that they've put planets where maybe sapient, sentient, like intelligent life has come from, like their homeworlds, like halfway or 2/3 of the way out. And the systems that you might visit closer in are often very turbulent, like crazy systems where maybe there was a recent supernova, or you have like some white dwarfs touching each other or something like that. I don't know. So we'll move on from Mass Effect, because I can talk all day about that, to another game. Everyone's favorite, Oddworld. Has anyone here played Oddworld? Yeah, it's kind of mixed reviews, right? So Oddworld is about this odd world that, from what I've read, I think, so it's like 10 times the size of the Earth, and like the mantle has collapsed several times, creating like underground layers or something. People can like yell at me if this is wrong, but anyway, what I was reading, it just didn't make sense to me, and it didn't sound very realistic. However, having a terrestrial planet larger than Earth is kind of realistic. We do have these things called super Earths. So we have planets. In fact, it turns out that they're probably the most common type of planet in our galaxy that are larger than Earth but smaller than Neptune or Uranus. Obviously, these are a huge source of interest. There's a lot that we don't know about them because we don't have an analog in our own solar system. But the particular example from Oddworld doesn't really make a whole lot of sense because it's 10 times the size of the Earth. And several years ago, a researcher named Leslie Rogers came up with this theoretical explanation for where you would expect the transition from something that's kind of more like Earth, more terrestrial, has land you can land on, to something that's more gaseous, more like Neptune or Uranus in our own solar system, where that would occur, and that occurs around 1.6 Earth radii, which is only going to give you like 4 times the surface area of the Earth. So actually, unfortunately, Oddworld, even though you got so much science completely wrong, you also got wrong that you could have a terrestrial planet 10 times the size of the Earth. It's too bad. So those super Earths, as I said, we really don't know what they're like, and that's a really hot topic within astrobiology and within astronomy in general. Some people think that at least some of these planets could be water worlds. And so we see these depictions of water worlds in games like Subnautica, that seems to be very popular with the kind of people I hang out with for some reason, where you have a world that's just completely covered in ocean, and in the game Subnautica you're exploring this, and there's maybe even some sort of like biological experimentation that's been happening on the planet. But these water-covered worlds, are they realistic? Possibly. We're not really sure because, as I said, we don't have an analog in our own solar system. What we're doing really is just kind of taking the density of the planet. So here we're comparing the mass to the radius, so the size of the planet compared to the mass of the planet, and looking at what density that should give us and comparing that to the average density of like silicate rocks, 100% water, some kind of mix with a ton of water, 100% iron, that sort of thing, and seeing what the composition of these planets should be like. So we have down here like Earth and Venus, things that are that size, and then these super Earths as we kind of move up to about 10 Earth masses, that would be a super Earth. And we see these things that are moving up towards a more pure silicate or even to like a very heavy fraction of water on the planet. So it's possible that these are completely covered by water, but it's also possible that that maybe there's some contribution from lighter elements there, and the ratios of like different types of rock on the planet can also affect where exactly on that plot you end up. So that's kind of realistic. Now we have No Man's Sky. Who here's played No Man's Sky? Wow, someone's clapping. I was very frustrated when I got No Man's Sky. I was told I could explore an infinite galaxy and that every planet would be different. And there was procedural generation, so like everyone else, I felt I was running around in circles and I just kept going to a new planet and being like, oh my god, this looks just like the last planet I was at and there's nothing to do and I don't know what to do and I don't know which direction the center of the galaxy is in. But, what was the point? Oh, right. But that got me thinking about rules for life, or if there are kind of like rules for life. So this procedural generation, we're kind of producing like some sort of pattern, some sort of algorithm with some variables that will produce different, biomes. I'm just going to stop him. With different types of, plant, flora and fauna type life on them. And they're kind of constrained because perhaps the procedural generation was a little bit too constrained and not variable enough in the first place. So is there something like that for actual life? Is there some rule to what life can do? This is something that Carl Sagan loved to explore. So he came up with this like cool exploration into what the life on a gaseous planet would be like if you thought there could be life on a gaseous planet. These like weird jellyfish things zooming through the atmosphere or poofing through the atmosphere. I guess we're not zooming. So this was the sort of thing that he loved to explore. He also explored, or talked about, I guess other people have probably explored things like how many fingers can you have before it just kind of becomes more of an impediment. If you have 6 or 7 fingers, is that really helping you or is it just causing more trouble? And so these ideas of whether there's like an optimum scenario are something that is central to at least some kind of thought experiments in astrobiology. And we know, looking at the fossil record, that we see these examples of the usefulness of different developments of things. So here we have a trilobite that's showing a mouth and eyes, depending, well, it's probably a different trilobite, depending which side you're looking at. And so these are indicating that this was a creature that was probably hunting for its food and chowing it down. So that's giving us some indication of the evolution of life, telling us changes that had happened at that time. So these sort of questions are really central. We want to ask, what are the rules? Does life always need to have complicated molecules? Does life always need to have molecules that maintain information well? Does it need to have molecules that behave in a consistent way so that it can interact with, so that they can interact with other molecules? Does life always move on to land if land is available? Does life always become predatory? Does life always diversify in the way it did on Earth? Does life always become intelligent? Is that something really central to like the physics of our universe? These are the kind of questions that astrobiologists are asking in like a very broad sense. Detecting molecules and elements on planets is something I don't see a whole lot in video games, but it's something that astrobiologists do, or try to do, hope to do. So there's this idea that you could look for particular molecules to maybe tell you that life is present on a planet. So you might be looking for something like oxygen, but you need to find these other molecules there too, and make sure that other particular molecules are not there so that you're sure that it's coming from life. And of course, what these signatures actually look like are these squiggly lines, and so that's what we're looking for when we take a spectrum of the planet, or of the planet with its stars subtracted through some method. I was so happy in Mass Effect when I saw that they had squiggly lines. It's a really sad thing to say. It's not exactly the same thing. These are like elements, which you wouldn't probably find through this method. But you're still looking at squiggly lines, and around the time that I was playing this, that was what I was looking at every single day. So it was really nice to see that somewhat accurately portrayed in a video game, and also the fact that they include noise in it is pretty cool. But yeah, so normally we're using this sort of thing to study the atmosphere, to look for what sort of gases, what sort of molecules are present in the atmosphere, not so much to look for the elemental abundance. That's something you can do more in situ. But from the surface, you could look for the reflectivity of the planet. So you could look for signatures from an ocean, as well as these kind of red edge signatures as you move through wavelength space, indicating that there's some pigment there that's doing photosynthesis. So you can extrapolate that life on a planet has developed photosynthesis based on its pigments and how they absorb light. The origin of life, I feel, also is not often dealt with a whole lot in video games. So some of them actually use this idea of panspermia. And panspermia, you've probably heard of, but it's this idea that some junk from another planet got yeeted off of it and flew through space and then like landed here and like somehow survived all of that. And then like diversified in this totally new, so depending who you ask, there's varying degrees of like how much people like this idea. But it is one idea that is considered for the origin of life, which is a central question in astrobiology. And in Spore, who here's all of your favorite video games? Who here's plays Spore? Yay! Oh, a ton of people. Okay. Yeah, so in Spore, the start of that game is a panspermia type event. So you're chucked into this environment, and then in the game, you get to kind of select your evolutionary developments to deal with your surroundings, determine whether or not eyes are useful and where they might be useful in your body. Sort of like with that trilobite I was showing you earlier, to deal with your environment, to move around, to maybe hunt and get food, and to mate. So that's a fairly accurate portrayal, although I don't know that some of the creatures people end up with in Spore are very accurate. Oh man, my bread and butter, good. Okay. So, not just the game, but I work in polarimetry, which relates to chirality, which I'll get to in a minute. So, in the game Mass Effect, I really hope you're not playing that game, the drinking game, I mean. I hope you are playing Mass Effect, to be clear. You have, these friends, all these alien friends, and some of them have a chirality to their amino acids that's different from yours. You would say that some of them have right-handed chirality to their amino acids, while others have left. And depending what planet you come from, that determines what sort of chirality you have. And the idea in this game is that this is almost like a very dangerous thing, that you can't eat the food from a species that has a different chirality from you. It'll make you very sick or even possibly kill you. And I thought that was a fascinating aspect to include. I hadn't seen it, although apparently it is in other sci-fi. I hadn't seen it in sci-fi before. So I was delighted that I was learning about chirality, and it was something that actually popped up in a video game, although it seemed a little bit overly doom and gloom. There are some cases where chirality flipping is a fine thing, and some cases where it's not. So chirality, just to be a little more clear, is the handedness of a molecule. So it's like a mirror image. If you flip it over, it's not exactly the same thing because it's a 3D thing. You know, something will go into the page that was formerly going out of the page, like your hands. You can't actually flip them and create the other hand. So we think that that is a really vital sign of life, that it might be one of the most agnostic biosignatures out there, because we think that life requires these complex molecules to store information and that they need to be able to interact with each other in a consistent and predictable way. In my work on polarization, we would be looking for circularly polarized light coming from these molecules. So when light is bouncing off the molecules, it's twisting the light just as those molecules themselves are kind of twisted, and that's potentially something we could detect, at least in our own solar system. So real life cases, first of all, the whole scare over drinking the booze from the Turians if you're human, or from the Asari if you're Quarian, is a little bit silly because alcohol itself isn't chiral. So no matter who you are, if you can metabolize it, then it's fine for you. It's like the booze of the, I guess there's other molecules in there, but the alcohol molecule itself from the humans is not any different from the alcohol molecule for Turians. There are cases where mixing up chirality has been really terrible. So in the late 1950s, I have to get out my cheat sheet. I don't remember drug names very well. That's why I went to physics. Okay, there was a drug called thalidomide that was given to people who were expecting to help them deal with morning sickness. And unfortunately, people found that that drug would cause birth defects of children, particularly in their limbs. Sorry, I just saw another person I know. So obviously that's a detrimental effect of mixing up the chirality. In that case, once this issue was discovered, people thought that, oh, it's just one chirality, one-handedness that's problematic. So if we just are more careful in our manufacture, we can produce just the one good chirality of that and continue to give that, maybe not to people who are expecting, but maybe to like cancer patients and other people who could use it who are not carrying and do not intend to have children anytime soon. Well, it turns out that, there's another word I don't know, that this stuff, thalidomide, does something called racinization. So it can actually flip its chirality while it's in a biological environment. So people could be given this drug and it could all just flip its chirality and become problematic again. So now, today, it is really only strictly given to people who are not expecting or who do not plan to have children in the near future, because this one chirality of the drug is so dangerous. At the same time, some examples of flipped chirality are perfectly harmless and even kind of helpful. So with sugar, I believe we usually eat D-glucose and sucrose, so D-dexter, right-handed. And there were efforts, I think in the 70s or 80s, to create left-handed or sinister glucose. And in spite of the name, that actually was a completely harmless as far as we know from the last few decades. Artificial sweetener. Basically what's happening there is that you're creating a molecule that, with its twist flipped, is no longer able to be metabolized. So your body's molecules that would normally tear that apart can't really latch on and tear it apart in the usual way. You don't get any calories out of it. So it's a good artificial sweetener. But the part of the molecule that interacts with like your taste receptors is still active and still able to make it taste sweet. So that was a great artificial sweetener. However, it was very expensive to synthesize. So that didn't really take. Just very recently, I guess, people have come up with a tagatose, a D-tagatose sweetener that mimics L-fructose. I don't know why I felt like I had to get every single one of those words exactly right, but I did. So anyway, this artificial sweetener that has a chiral that looks like something with a flipped chirality, so that your body won't use it for calories, but it will use it for taste. So there are examples of things that are very, very dangerous when you flip chirality, kind of similar to the Mass Effect universe, but there's also examples of things that are perfectly fine. Do you guys know the title? Brown chicken, brown cow? Does everyone know that? Right. So procreation, or the Frenchman told me I was allowed to say sex, with aliens is not really something that astrobiologists think about a whole lot, but I just kind of wanted to make sure that I gave a shout out to my friend Robin and telling me about the 100 baby challenge, which is a real thing for people who are into The Sims. Anyway, so in The Sims and in Mass Effect, you can hook up with and potentially create offspring with aliens. In reality, this procreation probably is not something that is likely to happen. Even if something had the same or like very similar DNA structure to us, it's unlikely that its genes, that like the way that sexual reproduction happens and that genes are passed on through us would translate to something else. Obviously, they don't even for other forms of life on Earth in all situations. So to do something like that, you would probably need to use something like genetic editing to get genes from something that's very, very different from you, incorporated into your own genome, and that's assuming that you even use the same general type of genome. In the game Mass Effect, Asaris like Liara are able to kind of not quite asexually reproduce, but they kind of create like a clone of themselves and then are able to manipulate their genetics through some sort of melding with the neurons of the other creature. It's all a little bit fluffy, it's not terribly scientific, but it is interesting in terms of astrobiology in the fact that both memory, both our neurons and our DNA are things that encode information for a long term, and at least in some sci-fi scenarios, could potentially pass them on. So ancient aliens is a super popular theme in sci-fi in general, and in video games especially. You know, it's also very popular on the History Channel, Aliens guy. It's something I guess that people are just interested in. But this isn't really something that an astrobiologist would be studying because it's not really something that's likely to leave behind any signs of it. Whether or not aliens ever came to Earth and visited, who knows? Because even if they left a structure, most structures on Earth only last for a few thousand years. It's part of the reason the pyramids are so amazing. They've lasted so long, and you certainly do not need aliens to explain how the pyramids happened. It's just humanity being amazing a long time ago. But this is a theme that keeps coming up, I guess because of public interest in video games. It's in Subnautica, it's in Destiny, it's in Mass Effect, and I've just included a picture of Star Child there for anyone who plays Mass Effect to make you angry. Yeah, I live for that. Yeah, so again, it's not really something something that astrobiologists are interested in because you're very unlikely to leave behind any signs of that. And certainly when we look at our own evolutionary path, both from the fossil record, and now we are able to use genetics to kind of fill in the gaps of that and correct little things, it doesn't really seem like there's necessarily any place that warrants this sort of explanation. Although I guess if people just came by and took a gander at us, you know, who knows, we would just never know that that was happening. Speaking of which, uplifting is also a theme that you come across in sci-fi. So in the game Mass Effect, there are these big stupid jellyfish called Hanar that just kind of idolize the Enkindlers, that's what they call them. The Enkindlers, these ancient beings that they view as gods that, you know, kind of uplifted them, that is, that helped their evolution, getting that to progress at a faster rate. Until they actually meet one of them, and then they, I guess everyone kind of thinks he's a jerk. But this is a common theme in sci-fi video games, so you see it in, this spoiler, in Destiny as well. There's a lot of spoilers on this one. Yeah, so you also see this in Destiny, of this sort of like malevolent entity that's moving around and helping creatures in different systems kind of move along largely by helping them terraform their planets. So there are these ideas throughout sci-fi, maybe helping evolution or helping people learn to write or improve space travel and things like that. And it's, again, just not necessarily something that an astrobiologist would be investigating because there's not really necessarily any indication of this from our own history, from our own evolutionary history, that requires this sort of thing. And it's not something we can necessarily look for evidence of. Now to the evolution of intelligence. So back to Spore here. Evolution in video games is often kind of simplified or glossed over. And one thing about sci-fi in general, and I would say especially about video games, that I find very interesting is that people almost always only have one intelligent species from a given planet. So it's just like, these are the so-and-sos of this planet, they are the sapient, sentient, intelligent race of this world, and they're all like this, and there's not a lot of diversity there, and you sometimes don't even get to hear about the other life that might have been around them. So it's like this very monolithic thing. But on Earth, of course, we've had like Neanderthals and Cro-Magnons existing at the same time in our past that were of, you know, relatively high intelligence. And even today on Earth, we have all of these different creatures that even by our own metrics, our own biased metrics, are still very intelligent, at least in some capacities. We also have examples of intelligence, and this is something that astrobiologists study, that are very evolutionarily separate from ours. So it's convergent evolution, so getting to the same endpoint through totally different means, totally different evolutionary means, which might be a good indication of something that is, you know, very central to life and central to evolution. But so cephalopods like octopi have created or have evolved these incredibly impressive neurological systems, completely separate from the sort of evolution of intelligence that we see to creatures that are more closely related to us. And I think that that's really fascinating. It's also very fascinating to me that the creatures that are more closely related to us tend to have a more social intelligence, while octopi, not all, but most octopi are solitary. They're not social creatures. They only really get together to procreate. I just find it personally very, very fascinating that you end up with intelligence that even we can recognize in both cases that's just super, super different, and from a very different evolutionary source. So for astrobiology, kind of exploring the breadth of intelligence is something that's really important to do. And plants do not have intelligence the way that animals do, but they do store information and pass information between each other, sometimes through a symbiotic life form. And I think that most people who study intelligence would agree with me that looking at the breadth of intelligence and, in astrobiological terms, of information storing and sharing is very central to this question of where we would find life in the universe. So we can't necessarily look for a planet that's just covered in elephants. Or maybe we could, that'd be weird. Or Neanderthals or anything like that. But if we're looking for life that's maybe kind of close to the level of progress of intelligence that we have right now, or further in the future, then we can maybe guess what sort of things those people, those creatures might be making. So this idea of a Dyson sphere is to completely surround, or eventually completely surround your star with basically like solar cells, something to take all the energy from the star so that you can use it. And this is kind of an old idea, and people in SETI have thought about this a fair bit. As far as the signature for that sort of thing, and it comes up in video games like Mass Effect and in Prey. I think you're actually on a Dyson sphere in Prey while you're trying to like not be killed. Which sounds terrifying. So the way that you would actually detect this sort of thing is looking for an infrared excess. So in this chart, we have the luminosity, basically like the brightness of the star compared to the color of the star. So red on the right, blue on the left. And you've maybe seen this sort of thing before. We have main sequence stars that are more or less like the sun along the middle here, and the sun would probably, definitely would pop up somewhere right in here. So for a Dyson sphere, for something that's from a star akin to the sun, we would expect that it's still just about as bright overall, but that light is coming out more red as infrared light because those cells are absorbing the shorter wavelengths and maybe re-emitting in infrared. Maybe they have better technology than we have and we wouldn't see anything at all, but this is an idea of a testable thing to look for. And some stars that kind of fall in this realm have been detected, as well as some other ones that look like they might have Dyson spheres through other methods. That's not to say there's definitely Dyson spheres, just to be clear. Okay, that person said definitely. So artificial intelligence isn't necessarily an astrobiology question, but it's definitely like a huge trope in sci-fi and in video games with a sci-fi flair. And they're often depicted, or artificial intelligence is often, and robots are often depicted as these scary things, maybe as like a final boss for you in Metroid, or something you kind of have to make like really hard decisions about in Mass Effect, or they're these kind of like swarm things, or nanobots that maybe kind of take over without meaning to, like in Destiny. But it's just often portrayed that artificial intelligence becomes this very scary thing for us. And I think that kind of like damning a hive mind is a little bit silly because we see examples of that on Earth, and there's not necessarily anything from a biological hive mind that's necessarily scary. We see that in bees and other insects, and I would argue, especially since the advent of the internet, we see that in humans. People all looking at, the same information that we're all sharing online and making a decision based on that. So it's not necessarily this terrible thing, I guess, the way that it's depicted in sci-fi, but there's probably people with other specialities who could talk even more to that. Expansion and Terra Formation is sort of like a little bit of an overlap with astrobiology, right? So in video games, we have depictions of this, like Eve, the Eve games, Eve Online, that are maybe suggesting that people are going out to do things like mine, and what sort of other careers would you find in a universe where maybe that's the main driver. In other games like Sid Meier's Alpha Centauri, which is one of the few video games I was allowed to play as a child, that you have these examples of Terra Formation in these games, as well as in some of the Mass Effect games, and they're often portrayed as this kind of like very easy, approachable, and benevolent thing. And in reality, for us to be terraforming anything nearby, I mean, for us to be changing the atmosphere of another planet would require that we understand and can control the atmosphere of our own planet, and we clearly aren't able to do that right now. But I think it's very interesting to see these depictions of what would drive people, humanity, and different aliens into space. And I think that the depiction of kind of commerce in space, maybe, and you see this in other sci-fi, based around mining of something that you couldn't find more easily nearby, that's the key, is a very probable gateway into outer space, into space exploration. So that brings me to colonialism in space, which is something that's not touched on a whole lot. It's something actually that astrobiologists and astronomers do talk about, decolonizing space and kind of inclusion within astronomy. Inclusion in video games, I would say, is slowly improving, and colonialism, I don't know of any particularly good examples, but when Mass Effect Andromeda came out, I was like, oh, this one's gonna do it. This one's gonna approach that question. Your old galaxy is completely ruined. You go to this new galaxy, there's tons of planets there that seem, ripe for the picking. You can terraform them. They're not that far off of what you want. And I was like, this is gonna be about colonialism in space. And then they were like, just like so-and-so is like angry at someone else, and so they're like, this other guy, and like someone else is there, and you're like, okay, but I'm going to like all of these planets that other people are already on. Are we not gonna talk about that? So I was a little surprised at that. If someone has an example of this, please like text me at the end. I don't know of an example of video game that really addresses this sort of thing, of what it means to be a human who's trying to spread out and maybe not being very careful about it. In astrobiology, something that we currently talk about a lot, that we do need to be very careful about, is contamination. There are kind of two main types of that. There's forward contamination, where we have something that's come from Earth on a lander or with a spaceship full of people on it, that is contaminating the other celestial body like Mars. And then we have back contamination, where maybe we've gone to Mars and we brought what we think is just a rock back, and there's ET organisms now, extraterrestrial organisms, that are in Earth's biosphere, or maybe if we were inhabiting Mars, that are maybe getting incorporated into our own biomes. So that's something, obviously, that we currently need to think about, even just sending a rover to Mars, or taking a small sample of what we think is just a rock back from another body. And maybe actually the Apollo talk might talk a little bit about how this is done for the moon. Possibly even more scary than back contamination, of bringing something back, because, it's unlikely, possible, but unlikely that some bug from another planet is going to be able to interact with your biome. You have, if you've evolved separately, it's unlikely that it's going to be well suited to attack you, to attack the particular types of cells, the particular molecules that you have in your body. But it's very scary to think about forward contamination, about just kind of accidentally sending something to Mars, and because you didn't hose it off properly, you've wiped out maybe this like lingering biome living beneath the surface. And there are different schools of thought on this. Some people think that the more robust extremophile from Earth that's kind of elbowed its way into its extreme, maybe super cold or super salty, or like low oxygen environment, will get to Mars and just be like, this is great and I'm used to fighting, so now you're all dead. But there are also people who think that, you know, whatever, if there was life on Mars, that whatever life, or on an icy moon or whatever life is there, is so well suited to its environment that it's unlikely that an outside form of life would be able to really knock it out, to influence it. It should have the upper hand. But that is an area of debate, and it's definitely, contamination in general is something that NASA, at least, perhaps not other people interested in space exploration, are very careful about. So with that, we'll finish up. I hope you guys will look for my friend's podcast, Mike Wong, who's right there. I won't shoot the laser at you. It's on SoundCloud. It's called Strange New Worlds. It's usually about Star Trek, so if this whole time you were like, God, shut up about video games and talk about TV sci-fi, you should really listen to it. And he has just one episode with me and another friend talking about Mass Effect, and then you can go listen to all the other awesome episodes, including one with Anthony Rapp, right? Yeah. And also, if you're going to Geek Girl Con, I'll probably be on a panel there talking about science and sci-fi with people who know more about the about like the biology, like the other parts that I probably totally screwed up here. So we'll have a panel there if you guys are coming to that. And thank you very much. I only have time for one question.
Halo is a great example of contamination.
Really?
Yeah, what?
Oh my god, okay, yeah, I didn't play Halo. Thank you very much. So that's a great example of contamination, you were saying. Thank you very much. I was afraid I'd do it a disservice. All right, thanks guys.
All right, welcome back for our second talk of the night. Thank you for bearing with us during some technical difficulties. For our second talk, I would like to introduce to you University of Washington astronomy professor and person who teaches stuff in his own words, and in my own words, who I think is undeniably the Apollo expert at the University of Washington. Please welcome Professor Toby Smith.
All right, good evening, and thank you. And just to destroy my credibility, I was the one clapping for No Man's Sky. It's awesome. All right, what I'd like to talk about today is for the last 8 days, we've been celebrating the 50th anniversary of the Apollo 11 mission, the first mission to the surface of the moon. 50 years ago right now, the astronauts are asleep inside the Airstream trailer in quarantine, which they'll spend the next 18 days, and the mission is ended. But for 50 years ago, and in our reflections over for the past 8 days, they've been talking about what Apollo 11 means, what Apollo 11 has done. And what I want to talk about today is that since this is nominally a talk about science, I want to talk about a little bit about the science from Apollo 11 and how it's changed our notion about what the moon is. But first of all, as we stare at this slide of the Apollo, one of the paintings of Neil Armstrong first stepping foot on the surface of the moon, I want to pay particular attention to the Apollo 11 patch. This particular story has been told, and it's been told in the newspapers before, and I just want to point out how unique that patch is for space flight. It's one of only 4 patches that does not bear the names of the astronauts, if you notice that. And it was very interesting, and this was a conscious choice. This quote from Michael Collins, the command module pilot for Apollo 11, points out, you can see here, that they wanted to keep their names off the patch, that Apollo 11 was bigger than the 3 people who were lucky enough to land on the surface of the moon. Apollo 11 was the whole nation going to the surface of the moon, and as he said there were thousands of people who could have taken a proprietary interest, yet would never see their names on the fabric of a patch. And I should point out that almost every astronaut has written an autobiography. There's only one that's worth reading. It's that one. The Apollo project's origin story begins a long time ago when John Kennedy went before Congress in 1961 to basically say that we were going to go to the surface of the moon. The amazing thing about this thing that happens in 1961 was that at that time, the US had 15 minutes of spaceflight experience. One suborbital flight, a lob off the coast of Florida into the Caribbean Ocean. At that time, they had to decide to go to the moon. And perhaps the most amazing thing about that is barely 8 years later, we land on the surface of the moon. We build the biggest rocket that's still ever been built. We built the rocket that has been the only rocket that's ever sent people out of low Earth orbit. All that happens in 8 years, and we land on the surface of the moon. One of the parts of his speech was that this flight and the whole entire mission was going to be done in front of the whole entire world. And as we've seen in the last 8 days, if we reflected back over the past 50 years, is that this perhaps is Apollo 11's greatest legacy. Because as I look across this crowd here, we see people who remember this in real time. We remember people like me who saw it but don't really remember it. And people who are never alive during that time. What is interesting about Apollo is how much of a shared experience it was. That the whole entire world was watching this, and there's very few events that the whole entire world watches. What's interesting is that the Apollo 11 broadcast in the United States is still the most watched thing on television. This table is a little bit scary, I always think. When you look at the things that are the most watched thing on television, that the vast majority of them are Super Bowls. And I also find it interesting that the only 2 TV shows are MASH and Roots, dating back to the 80s and dating back to the 70s. But up there on the top is Apollo 11. However, you shouldn't get the idea that all Apollo missions were equally as followed. The Apollo 11 mission was, as we found in the last 8 days, an amazing mission. 14% of the world population watched this. In a lot of respects in the United States, because it always happened at such nice times. The launch, the landing on the moon, the first footsteps, and splashdown even happened at reasonable times. Especially here in Seattle, it's basically prime time. That the first steps on the moon happened at 8 p.m. local time, and so it was sort of not planned, but it worked out that it happened to work out in very well-timed places that a lot of people watched this. However, like I said, you shouldn't get the idea that this was normal during Apollo. The press coverage of Apollo 11 was far, far out of scale of everything else. As you see in this little chart, I just made this little chart where I sort of made a look at all the mentions of the Apollo missions in the New York Times, because it was an easy database to search. And what you see here is after Apollo 11, the coverage of Apollo just dives down exponentially. By the time Apollo 16 is happening, it was barely covered. It wasn't shown on television hardly at all, and it was just barely covered. Part of the result of this is that after Apollo 11, it's only 3 years and 5 months, that Apollo 17 splashes down in the ocean in December of 1972 to end the Apollo missions. The Apollo program was really short. From the landing on the moon to the last landing on the moon was barely a college career, as I say during my class. In this little timeline of the 20th century, the first flight of Apollo to the last flight of Apollo is shown in red. It's a very, very small fraction of the 20th century. In terms of space flight, since we've been throwing things off of the surface of the Earth, Apollo represents a very, very small fraction of that. However, it is the only fraction where human beings have left low Earth orbit. Before that red square and after that red square, no human beings have ever left low Earth orbit. We've thrown a lot of people into low Earth orbit since that time, but never after that time. I do have to make this proviso, is that you always have to remember, as I'm talking about this, that the Apollo mission was from beginning to its end a political mission. There's only one reason Apollo exists. It exists to beat the Soviet Union to the surface of the moon. Without that, you do not go to the moon. I've often said that the Apollo program is a weird mission. It is a mission that should be happening about today, but was pulled back into the 1960s because of the politics. It happened at perhaps the only time in the later 20th century that it could have happened. It's an amazing thing to think about, to convince not only people to spend the tax dollars to go to Apollo, but to plan a mission that would last over many presidential administrations, and each one of them would support it and not just rapidly cut the funding and kill the program. However, what I want to talk a little bit about today is that although science is never the driving factor of Apollo, it was never the reason Apollo goes to the surface of the moon. In fact, it wasn't fully embraced by the scientific community even in its day, even among planetary scientists. However, since we were going to go to the moon, people were going to land on the moon, people were going to come home, you might as well do a little bit of science, or as much as you can jam in the little bit of time that we had. And what I want to talk a little bit about today is that this little bit of science they did fundamentally changed how we view not only the moon, but the Earth-Moon system and our solar system. So much science comes out of Apollo over the last 50 years. The amount of science that's been published on the Apollo missions and the results of the Apollo missions just fills libraries. However, it starts 50 years ago. It starts with the landing of Apollo 11. One of the interesting things about Apollo 11 was how short it was. The Apollo 11 mission was only 8 days, barely over a week, from launch to splashdown. The amount of time physically on the moon of the two astronauts was not even 24 hours, 21 hours. Very short amount of time. And the physical amount of time out of the spacecraft was about as long as you'll probably be here tonight, a little over 2 hours. That's a really short amount of time, and a really short amount of time to jam whatever sort of things you want to accomplish on the moon. I should point out that Apollo 11 was by far the shortest of the Apollo missions. Here's the other 5 Apollo missions, and you can see here that by the end they were spending almost 36 hours on the surface of the moon, and the missions lasted almost 2 weeks. Apollo 11 up there on the top, by far the shortest of the Apollo missions, but it's the one that people hear about because it was the first. Those 2.5 hours on the surface of the moon, the vast majority of time was spent, I guess, what I would call doing the mechanics of a spacewalk. The photographs, the documentation, the physicalness of getting out of a spacecraft, getting down onto the surface. I try to show that here. This is the timeline over 2 hours and 31 minutes that they were on the surface of the moon, and the mechanics is sort of shown in, I guess, the bluish color. The science-y bits that I want to talk a little bit about today are in red. And what you can see there is they represent about 1/3 of the time that they were on the surface of the moon. If you add up those times, those add up to about 45 minutes. About as long as I'm going to talk is what we would call the science-y bits of Apollo 11. And you can see they were broken up into picking up stuff and setting up stuff. Picking up stuff in the beginning, and then near the end they spent about 30 minutes setting up some stuff. So you can see the total amount of time they had on the moon was very limited. Time was the big constraint of all the Apollo missions. And so they had to jam in as much as you can in that short amount of time. As you saw in trivia, Apollo 11 was unique in the Apollo missions in that Apollo 11 actually had 3 landing sites ready to go. Meaning that if they couldn't launch on their first launch site, July 16th, instead of waiting a month for the Earth-Moon to get back into alignment, they could just move to a different landing site a little bit farther to the east, or to the west, I'm sorry. However, they did launch on their first launch on July 16th, and so they landed on, in here, the rightmost, what we call the eastmost side of the moon, in what's called a mare surface, a lava flow called the Sea of Tranquility, Mare Tranquillitatis. A featureless plain that consists of a large flow of lava, cooled volcanic rock. A place that superficially would remind you of, think of the big island of Hawaii. Think of the big lava flows, the fresh lava flows on the big island of Hawaii, and give you an idea of what you would expect at the Apollo 11 landing site. However, one of the important things, and one of the things that is in some ways not most difficult to understand, but people who most understand about the moon, is that the moon is not the Earth. And although I can say that the landing site are lava flows that look like the big island of Hawaii, the moon is not the big island of Hawaii. For 4.5 billion years, it's been a very, very different place. And perhaps the most obvious difference is that when you look at pictures of the moon, they all look like this. The moon looks soft. The edges have been rounded off. There are no mountains that look like Mount Rainier. There are no mountains that look like the Grand Tetons. There are no sharp peaks. There are no sharp edges. The reason is that for 4.5 billion years, the airless moon has been impacted by objects of all sizes. Not just big things that could punch through the atmosphere like the Earth, but even the smallest grains of sand are continually raining down onto the surface. 20,000 tons of stuff hit the moon every year, grinding the moon to a soft powder. As a matter of fact, this was the second line Neil Armstrong said after his one small step business. This was literally the next line. As he looked down at his feet when he made his first step, he said, "The surface is fine and powdery. I can kick it loosely with my toe. It adheres in fine layers like powdered charcoal to the soles and sides of my boots." This superficial covering of the surface of the moon has about the consistency of flour. When you put your footprint in, it sinks about 1 inch, but it makes very definite footprints. It's not like your feet at a beach where you step on sand and then your footprint quickly erodes as the sand cascades back in. This is a surface that will preserve a footprint. That footprint, this particular one is Buzz Aldrin's, will preserve this footprint for millions of years. This surface that they're on is sometimes referred to as lunar soil, but soil's the wrong word. soil has a very biological context. On the moon, this covering is called a regolith. It comes from the Greek word meaning basically blanket of rock. It's a layer of loose superficial impact-generated rock that covers the whole entire surface of the moon and has reduced the whole entire surface of the moon to this fine powder. What that means is that every structure on the surface of the moon has been reduced to this powder. What that means then in 4 billion years, everything we've landed on the moon, the descent stage of the Eagle spacecraft, the backpacks of the astronauts that were thrown out at the end, will be reduced to a powder. The slow, continual bombardment of the moon is reducing the surface of the moon to the powder. So that everything on the moon has this soft, subtle sort of appearance. And the little bit of science I want to talk about is about this little loose covering of powder of all things. Because about 70 minutes into the mission, after the astronauts set foot on the moon, after they planted the flag, after they talked to the President of the United States at the time, they had 15 minutes. The commander of the mission, Neil Armstrong, spent 15 minutes doing what is called the bulk sample collection. What did he do for 15 minutes? Just outside the spacecraft, right between where he stepped off and where they planted the American flag. You can see all the footprints that I tried to show in there. Right in that little area there, he spent 15 minutes, as fast as he could, chucking rocks into a box. Here's the box. It's very fancy looking. Stainless steel box with a little aluminum mesh interior that is supposed to essentially take the rocks back to Earth, seal them from the rest of the Earth, and he just chucked the rocks into this box. Here they are. They're not super impressive looking. They're rocks. And when people see moon rocks for the first time, they have that same idea. When you get this idea that moon rocks are these weird extraterrestrial things, when you actually see a moon rock, you find out they're really not that interesting looking. When the Apollo astronauts came back, the first rock went on display at the American History Museum in New York City. When millions of people went and looked at this rock, shown over there on the left, people like to look at this rock, but all the, basically, the press for this rock, when they talked to people who saw it, all said the same thing. It's a rock. Not light, not dark, it's gray. It's just gray, gray rock. One of my favorite pictures over there on the right, in the Lunar Receiving Laboratory where the rocks came back, one of the first things the scientists did when they opened the boxes was they wrote down a quick paragraph of what they see before anything gets changed. They tried to describe the rocks, what they look like, what they're made of, what the crystal structure is, et cetera, et cetera. They were given a guide for color of the rocks. That guide is over there on the right. That's a colored picture if you can't see it. What's more interesting is if you take a look at the back, shows the colors themselves. Starting at the top, gray, gray-black, dark gray, medium dark gray, medium gray. That's the color of the moon. The moon is very monochromatic in terms of its rocks. They're all shades of gray. However, it's not even those rocks that Neil Armstrong chucked into the box that I want to talk about. It's this. Every sample that comes back to the Earth gets a zip code that uniquely identifies the sample. It's a 5-digit number that changes with each mission. This particular sample I want to talk about here is 10084. It was collected after Neil Armstrong chucked all the rocks into the box. He scooped up 9 scoops of soil and threw them into the box as packing soil, so the rocks didn't bump around. You can actually see it in the picture. I've tried to highlight it here. You can see amongst the footprints, you see some of these deeper gouges. If you count, there's 9 of them. That's where Neil Armstrong scooped up 9 scoops right there, chucked them into the box so they wouldn't bounce around. What is interesting about this sample was when it got back to the Earth, the rocks were pulled out. That's the picture I showed you. In fact, do I have another one? There they are. That's the first time it was opened in the Lunar Receiving Laboratory in Houston on the left there. When the rocks were removed, that regolith was separated. And there was lots of it. In fact, you can see there was almost 4 kilograms, 15 pounds, something like that, of lunar regolith. This material was then widely distributed to scientists all over the world. As I said in the little blurb there, it is perhaps the most studied geological sample on the Earth, certainly by pound in terms of in terms of study. This is what it looks like close up. Like I said, it has about the consistency of flour. It's a fine-grained material. You can see it here. You can see the human fingerprints down, the human fingers down there for scale. If I were to zoom in on this, here's what the pieces look like. What you notice is two things. One, size scale up there on the top. That's 2 millimeters, about a 1/16 of an inch roughly. So you can see all the pieces are small. But you see something else, that unlike sand, all the pieces are highly angular. This is not material that was broken up by being tumbled. This is material that was broken up by being fractured by impacts. The lunar soil is very sharp. Think of shards of glass. When you look at this particular thing, you can also see that the lunar regolith is very diverse. There's lots of different pieces here. There's pieces of basalt. This is the volcanic rock that makes up the Sea of Tranquility landing site. Those little pieces I'm showing there are pieces that were broken up over the last 4.5 billion years. There are pieces of material called breccia. This is material that is created when an impact hits the moon and material is shattered and remelted together. It sort of looks like a jigsaw puzzle sort of smashed together. It is perhaps the most common type of rock on the surface of the moon. There's material that has been melted by impacts. Sometimes it's melted into blobs, sometimes it's melted into perfect little spheres. They're called impact spheres. Most of this material that you see is all indications of material that has been affected by these impacts. However, right there in the center, the reason I just framed the picture I did in this way, is this weird little rock. You can see it's barely big, it's not even 2 millimeters across, but it sort of stands out because it is this sort of bright white color. And it is this rock, of all the pieces that people dug through in this sample, that turned out to be the most unusual. And perhaps the only one amongst the lunar regolith that was unexpected. It's a material called an orthosite. It represents a piece of the original crust of the moon, long since destroyed by 4.5 billion years of impacts. A foreign little piece that was tossed to the Apollo 11 site, scooped up by Neil Armstrong and brought back to Earth 50 years ago today. After the samples were returned from the Earth, scientists spent 6 frantic months making the first analysis of lunar rocks, quickly writing papers at a pace that is unheard of, and 6 months after the Apollo 11 mission, published a special issue of the journal Science, devoted to the Apollo 11 samples. On the cover, which is shown over there on the left, is a small little sample of this sample, 10084. In this journal was a paper that had the simple title called Lunar and Orthosite, written by a team from Harvard, the Smithsonian Institution. And I pulled one line out of it here. Is one, you see most of it is material that's been beaten up, called breccia, pieces of the Sea of Tranquility, basalts, but there's 4% of it is this weird anorthosite. And it was only this anorthosite that was totally unexpected. It was perhaps the biggest unexpected thing of maybe not the whole entire Apollo lunar collection, but certainly Apollo 11. But why was it not expected? Oh, it even made the New York Times. Strange particles found in lunar sample. It was popular enough that it even made the New York Times, which I thought was awesome. What is unusual is that this weird anorthosite is what's called an igneous rock, just like basalt. It comes from volcanoes. Oh, sort of. It comes from cooling of melted rock. I guess that's more technically correct. However, what is unusual about this sample and why it was completely unexpected is that basalt comes from lava flowing across the ground, cooling hard, and you have basalt. Again, think of the big island of Hawaii. However, there's no such thing as anorthosite lava. You can't have lava going across the ground, cool, and ta-da, have an orthosite. Anorthosite forms in a very, very specific way. And it was this weird specific way that made this weird little, tiny little fleck of this tiny little pile of dirt from Apollo so unique. Anorthosite forms in big pools of lava, huge pools of lava, huge chambers of lava. As these chambers of lava slowly cool over time, the anorthosite floats to the top to form a crust. If this was found on the moon, it must mean that at some point the moon was almost completely molten. That at some point early in the moon's history, it must have been almost completely molten so that anorthosite can float to the top. It's the only way it forms. This was very surprising to the Apollo scientists, because before Apollo there was no indication that the whole entire moon was almost completely melted. And it was right here in this paper that came out in the beginning of 1970 that starts the idea that the moon's origin must be weird, because however you form the moon, you have to form it so energetically that it completely melts. As probably a lot of you know, the current idea of how the moon forms is that early on in the Earth's history, a Mars-sized object crashes into the forming Earth, and that the debris of this impact forms the Earth-Moon system. Modern computer simulations have shown that this happens sometimes. Pretty low probability, though. In most of these computer simulations, if you smash a Mars-sized object into the Earth, 98% of them basically just end up with a slightly bigger Earth. This is actually a low probability event to actually get a moon from this particular thing. But this idea of a giant impact to form the Earth-Moon system begins with that small fragment of anorthosite in the little scoops that Neil Armstrong just chucked into the rock box so the rocks didn't rattle around as they came back to the Earth. A fundamental change in how we think about the moon happens by studying this really small little sample, digging through little flecks of regolith, little fragments of rock, finding stuff that's very unexpected, and fundamentally changing about how we think of the moon. I said here that this particular sample, 10084, this almost 4 kilograms of regolith that was tossed in the box, is one of the most studied samples of any sample on the Earth. Certainly by pound, it is the most studied sample. I just quickly went to the astronomy database and found, I think, almost all the papers I could find where this was the main rock of study of a paper. And what is interesting is that the Apollo 11 missions happened in 1969. This sample was collected 50 years ago today. The first papers came out in 1970, but as you see here, they just keep on coming out. In many ways, this is one of the best legacies of the Apollo project, because the samples are here. Since people had to come back, you might as well bring rocks back with you. And if the samples are here, they aren't going to change. The vast majority of Apollo samples have never been studied. And that's for a very, very specific reason. Because technology will change. Our interpretations, our instruments will get better and better, but the rocks will always be there, so we can always restudy the rocks. This sample, like I said, has been studied, and 1, 2, 3, 4 papers came out last year looking at this sample, this little pile of regolith that was collected by Apollo 11 using brand new techniques. Oh, I like this. And the generation of scientists who are studying the rocks have started to change, which is excellent. Just recently, a month ago, 2 months ago, I forget when it is, NASA just announced the next generation of Apollo analysis. They keep on being studied 50 years later. The Apollo Next Generation Sample Analysis teams were announced, and now samples, pristine samples, will be released to the next generation of scientists using the next generation of technology to dig out even more information, again, in this little handful of soil. It's insane how much information is being pulled out of this little handful of soil. And I should say that this technique that starts with Apollo is continuing in spaceflight today. I just want to do a quick little advertisement here because this will be awesome. Currently, NASA has a mission called OSIRIS-REx. It's a horrible acronym, but what the hell. That is going to a weird little asteroid called Bennu. which is basically a weird little bag of gravel in space. It's only about 4 kilometers across. It's a tiny little asteroid. But what's interesting is exactly 1 year from today, I think it's July 24th is the sampling date. It could be the 25th. A year from now, this spacecraft will drop down onto the surface and scoop up a bunch of soil. In very much the same way that Neil Armstrong chucked some soil into that rock box. In September of 2023, that handful of soil will come back to the Earth, come to the Lunar Receiving Laboratory in Houston, be distributed to scientists around the world, and another story will be told, but a story about this asteroid Bennu using the same idea of looking for little unexpected things that you wouldn't expect to find in this weird little asteroid. They have lots of close-up pictures of this thing, and as it gets closer and closer, it just looks more stupid. It has no reason to look like it does, I just want to say. To finish me off here, as we're ending this night here, as we've celebrated over the last 8 days, the 50th anniversary of Apollo, I just want to say a few things, and one is this. There's lots of people there, I've just noticed as I was walking around, who have this emblem on them, either on a shirt or something like that. And just that idea seems utterly insane. Think of one other government organization whose t-shirt you would buy with your own money and wear all of the time. There's not a day that goes by that I'm not on the metro buses and there's not somebody wearing a NASA t-shirt. That's an insane amount of goodwill that is done. And in many ways, the goodwill of NASA, for better or worse, comes back to the Apollo projects. Perhaps the most iconic picture ever taken by Apollo was taken in Christmas of 1968 by Apollo 8. Earthrise over the moon. 25 people have seen this. Over 4.5 billion years of organisms on the Earth, only 25 people have seen this. 3 of them twice. It'll be a shame if, into the future, it's still that number, only 25 people. Only 27 people have ever left low Earth orbit. And in the 50 years, that number has not changed. The last of the legacy of Apollo is this idea that even 50 years later, and it's hard to think of something that happened 50 years ago that is still used as the bench for doing good things. It's hard to find something that was made 50 years ago that has this legacy attached to it, that is the pinnacle of what you can achieve. Whether we achieved it for the right reason or the wrong reason, that's irrelevant, but it happened. And it's amazing that 50 years later, we are still celebrating this, and that just a handful of dirt fundamentally changes how we think of the moon. All right, thank you very much. Couple questions? Oh, yeah.
If the white rock is such a small percentage of the regolith, why wouldn't there be more if it was the entire surface?
So the question is, the white rock, it was such a small percentage of the regolith. Why wasn't it the whole entire part of the moon? It was the original crust of the moon, but the Apollo 11 landed on a Mare surface that has covered up that old surface about 1 billion years after it formed. And so that particular piece was thrown from far away from the surface of the moon. And since about 4% of it, that's about what you'd expect from distant material that was thrown onto the site. If you land, Apollo 16 landed on the highlands in that heavily cratered area, and every piece was a northern
Thank you.
And then this is a silly question, but why does it take 3 years for the sample to return? Isn't that far? Is that asteroid so far?
Yes. Yeah, so the asteroid's out beyond the orbit of Mars and Jupiter, and it's not a direct flight. You have to wait for everything to line up, so you collect, wait for the planets to line up, and then come home. Going to the moon is easy. A couple of days. Going farther is so much harder. When people say about, oh, we want to go to Mars after going to the moon, oh my God, it's so much harder. 3 days to go to the moon, about 1.5 years to go to Mars. So it's not the same thing in any way, shape, or form. I just want to say that. Yeah.
So you talk about the Apollo 11 sample return. What about the other missions? And what did they bring back, and what did we learn from those?
So in some ways, I'm doing it sort of backwards here. But the question was asked, what did the other Apollo samples teach us? And basically what we find as we go on to the Apollo missions is that we find different pieces of the moon are different. It's not all formed at the same time. There is some locality. The Mare surface Apollo 12 lands at is different than Apollo 11 lands at. We find big pieces of this anorthosite. Apollo 15 returns a rock that's very famous called the Genesis rock, which is this big hand-sized piece of this anorthosite. Apollo 16 returns nothing but anorthosite, essentially. So basically, it tells us the story locally of each particular mission.
So there's a crater on the moon that you see it all the time.
Tycho.
Tycho, did that land on the original crust?
So Tycho is basically the last crater, the last feature of the moon we could have seen form. It formed during the time of the dinosaurs. The dinosaurs would have seen that form. And that hit the old highlands of the moon. And that's actually one of the best places to find this original crust. Unfortunately, it was way outside where Apollo could land. The last Apollo mission made a strong case to try to land that, but the engineers wouldn't let them do it. All right, thank you very much.
All right, thank you,